Good. Okay, so we're very happy today to have Mike Crommie giving a seminar. Let me give you a brief introduction. Mike got his PhD in 1991 from UC Berkeley, which is sort of appropriate. Then went on to do a postdoc with Don Eigler at IBM Almaden, and then went to start up as a professor at Boston University. He returned to Berkeley in 1999, where he's been ever since. He's won a number of awards, including a Sloan Foundation Fellowship in 1997. Mike's an expert at using cooled scanning tunneling microscope to really manipulate single atoms and to make individually built molecules and the like, and then to use the instrument to look at quantum materials to uncover. I can't talk today, to uncover how they actually work. Today is going to look at a very interesting system, which is a spin liquid, a bunch of closely interacting spins that theorists have worried about for some time, but it's very difficult to access experimentally to figure out what really goes on, and that's what we'll be telling us about today. Mike.
Great. Bob, thanks a lot. Can you hear me okay, Bob?
Yeah, that sounds great.
Okay, fabulous. Okay, folks, so I'm going to start. So today what I want to do is tell you about some recent work that we've done, which has uncovered evidence for quantum spin liquid behavior in single layer 1T TSE2. And can you see my cursor as I move it around? Is that visible?
Yeah.
Fabulous. Okay. All right, so here's an outline for my talk. First, I'll say some introductory words about quantum spin liquids, and then I'll talk about how single layer 1T TSE2 satisfies the requirements of a quantum spin liquid, which I list here. Then I'll talk about how we've actually seen direct evidence for quantum spin liquid behavior in this material. More specifically, we've observed long wavelength modulations that we believe are a signature of a spin-on Fermi surface instability. So what is a quantum spin liquid? Well, a key ingredient is you need a highly frustrated spin lattice. An example is a triangular lattice. And if you have spins on the triangular lattice that are antiferromagnetically coupled, then if you put two spins here, they know what to do. They go like this, up and down, but the third spin doesn't know what to do, whether to go up or down. And so that's frustration. And so that leads to interesting behavior on lattices such as the triangular lattice or the Kagome lattice that show frustration. They have interesting classical magnetic behavior, but they also have interesting quantum behavior. For example, they lead to quantum spin liquids. And to understand what a quantum spin liquid is, I think it's useful to first show what is not a quantum spin liquid. This is not a quantum spin liquid. Here I'm showing you the Néel 120-degree rotated antiferromagnetic state. It's not a quantum spin liquid because it's not entangled. I can write this down as a product state. It shows magnetic order. It has magnetic order. And also the expectation value of spin at every lattice site is not zero. So that's not a quantum spin liquid. Now take a look at this. This is the famous Phil Anderson resonating valence bond state. This is a quantum spin liquid. What we have here is all the spins are coupled into singlets. That's what these gray ovals are. And the state is then a superposition of all the different possible singlet arrangements. This is highly entangled. I cannot write this as a product state. It has no magnetic order, and the expectation of spin at every lattice site is zero. So that is a quantum spin liquid. Those are characteristics of a quantum spin liquid. Another characteristic of a quantum spin liquid is that often you get fractionalization of the particles. In other words, the electrons can split apart into neutral spinons that are fermions and spinless charge-ons that are bosons. And in order to see this in sort of a qualitative way, let's consider this RVB state in the lower left part of the screen. Let's remove an electron, and that leaves a charged holon and a neutral spinon. And then by rearranging the singlets, you can imagine how the holon and the spinon start to decouple. And so that's how you can get spin charge separation in sort of this cartoony way. Now, there are a lot of quantum spin liquids that people have been studying over the last 10, 20 years. Here I show some of them on this table. They have different lattices, different materials, different symmetries. Some are gapped, some are gapless. So there's a whole bunch of them. And so what I'm going to do today is I'm just going to stick to this one type, which is gapless quantum spin liquids on a triangular lattice with U1 gauge symmetry. This is the only one that I want to talk about today. So how might such a quantum spin liquid arise? Well, to see that, it's nice to start with the Hubbard model. So let's consider a triangular lattice that's half filled 1 electron per site, and then we can describe it with this Hubbard Hamiltonian. Now this parameter T describes the kinetic energy. That's the hopping amplitude, describing how an electron can hop from one site to the other, whereas U is the Coulomb repulsion, the energy of double occupancy. Now in the limit where U is way bigger than T, then we get a strong Mott insulator, and this Hubbard Hamiltonian can reduce to this much simpler Heisenberg Hamiltonian that I write here. Now, in this case, the ground state is going to be the Néel order, the 120-degree rotated antiferromagnet, and that is not a quantum spin liquid. But now let's reduce the U. Let's reduce the U parameter. We're still in the Mott regime, but let's reduce it. Now we can get additional terms in the Hamiltonian, such as this ring interaction term that I show here, which couples together 4 spins on a plaquette, as I show in this upper right. Now, this ring interaction provides additional frustration that then induces the system to fall into a quantum spin liquid state. At least this is what's been predicted. What has also been predicted for this type of system is that you get charge fractionalization, where the electrons fractionalize into the spinless charge-ons and the neutral spin-ons. Now the charge-ons, we expect there to be no charge-ons. We have this filled band in the bottom. There's no holons. There's no doublons. We expect that to be empty because of this Mott gap. On the other hand, the spin-ons are fermions, and they fill the spin-on band only halfway. And the spin-ons are like free particles that can just move around, like free electrons. and they have a Fermi energy, and they also have a Fermi surface, which you see here on the right. This red circle is the Fermi surface. It's sitting inside of this hexagon, which is the Brillouin zone for the triangular lattice. And these green arrows are the reciprocal lattice vectors of the triangular lattice. And so this should remind you of a free electron gas. It should remind you of a free metal on a triangular lattice. In fact, it is just like that, except it's a special kind of metal because there's no charge. So it's this really weird thing. It's this neutral metal that is living inside of an insulator. So it's a very strange object. And also has an additional funny property, which is that even though the spin-ons are neutral and we cannot grab onto them with external electric fields, they actually feel each other through an emergent gauge interaction due to the U1 gauge symmetry. And so that means that they have gauge charge. So it's sort of like they have their own internal Maxwell's equations inside the quantum spin liquid, but we cannot grab onto them from the outside. So it's a really strange system. And so the question then is, how do you actually observe this kind of behavior? And so one way of doing it is to use thermodynamic measurements. For example, a trick that people do is to look for signs of metallic behavior in insulators, such as a linear temperature term in the heat capacity, or a linear temperature term in the thermal conductivity, are signs of quantum spin liquid behavior that people have seen. You can also look for this behavior of spin-ons in inelastic neutron scattering, as I show here. But one thing that's hard to do is to map the Fermi surface of a quantum spin liquid, because you cannot use typical tricks like Shubnikov-de Haas oscillations, because you can't perform electrical conductivity. So what I want to do now is tell you about a new technique that we can use to see signs of the spin-on Fermi surface, which is scanning tunneling microscopy. So it's sort of an old technique that I'm repackaging as a new technique because we're looking at a new material with it. Okay, so let's talk about STM for a moment. Conventional scanning tunneling microscopy is where you put a voltage on the STM tip and you tunnel electrons into a material. Now, normally the rate at which the electrons tunnel, which determines the electrical current, is going to be proportional to the wave function of electrons at the surface. And this is just the standard Tursoff-Hammond interpretation that STM people know and love. But things are a little different for a quantum spin liquid, because now when an electron tunnels into a quantum spin liquid, it breaks apart into 2 particles, a charge-on and a spin-on. And so now the rate at which the electrons tunnel is going to be proportional to the product of the spin-on wave function times the charge-on wave function, just because of the simple probabilistic nature of making 2 particles at the same time. And so what that means is that if there's spatial modulations in the spin-on wave function, then we should be able to see them by simply scanning our STM tip and measuring spatial variations in the STM tunnel current. So why then haven't you seen dozens of STM papers where people claim to see spin-ons? And the reason for that, of course, is because the quantum spin liquid is in an insulator. It's in a Mott insulator, and you cannot do an STM. You can't do a tunneling experiment on an insulator. You can't get the electrons in and out. You need a conducting surface, and that's why you haven't seen lots of papers on this. But it turns out—
I had a question, Mike, from Casey Fong. Says, is the temperature dependence of heat capacity definite proof of QSL?
No, I would say it's not proof, but it will be a signature. I mean, so people have used that as a signature because basically that's a signature of a Fermi surface. You know, if you in a metal, if you have a Fermi surface, you expect a linear term in the heat capacity. And so normally for an insulator, you don't expect that. So if you have an insulator and then you see that, then you can say, oh, this is potentially a signature of some ghost metallic state inside of the insulator, i.e. a spin-on Fermi surface. Does that make any sense?
Great.
Yeah.
Sounds good.
Okay.
Thanks.
Okay. All right. So let's see. Okay. So normally we could not see the quantum spin liquid with an STM tip because we can't tunnel the electrons in it. But we can do a trick. If we have a two-dimensional material and if we put that on a conductor, then in principle, we could tunnel into the quantum spin liquid and drain the charge out of it through the conducting surface below, because if we have the two-dimensional material is so thin. But this is tricky because you need just the right type of two-dimensional material. You need a material that satisfies the criteria of a quantum spin liquid. It has to satisfy these three criteria. You need a frustrated lattice, you need a 2D Mott insulator, and you need localized spins. Now, I realize these two last ones kind of go together, but I find it useful to separate them. So now what I want to do is to introduce you to a new material that we believe satisfies these three criteria, which is single layer 1T TASC2. So what I'm going to do is I'm going to spend a little bit of time showing you how this material satisfies these three criteria, and then I'm going to show you some direct evidence of quantum spin liquid behavior. And so let's talk about this material for a moment. 1T refers to the structure of the material. It's a transition metal dichalcogonide. The tantalum atoms are octahedrally coordinated amongst the selenium atoms, as you see here. This is the side view of the unit cell. A single layer of this material actually is a tri-layer where the middle layer is tantalum sandwiched by a top layer of selenium and a bottom layer of selenium. This on the left is the top view. The tantalum atom is in a 4+ state, which means that it only has one d electron in each tantalum atom. So that's nice. It's kind of simple, just one d electron. There is a nuance, which is that this material has a charge density wave, which is driven by electron-phonon interactions. It's a Star of David charge density wave. The unit cell is a Star of David, as I show here. So and there's 13 tantalum atoms in each Star of David cluster, and so that means that the material is really a superlattice, and the relevant lattice that we care about is the lattice of the charge density wave. And I've drawn in this red triangle, and in fact, it's the center atoms which are the ones that we care about. So those are the important guys. So what this means is that this material does satisfy this first criteria, which is it has a nice frustrated lattice, a nice triangular lattice. So that's good. But is it a Mott insulator? Now, that is not obvious because if you take bulk TASC2, it's a metal. As I show here, you can see the resistance versus temperature is metallic. And so that's pretty far from being a Mott insulator. But surface science people have shown that at the surface, if you look at the surface of this bulk material by STM or ARPAs, it does show signs of insulating behavior. So it's kind of a complicated material. And what makes it complicated is the interlayer coupling. That's complex. Now, at this point, I want to tell you about another material, the sister material, which is very famous, 1T-TAS2, where the selenium is replaced by sulfur. This is actually a more famous material because it is a bulk insulator. And in fact, people have seen evidence in the past that it is a Mott insulator. This is some STM data, which I think comes from Yayu Wang's group, where they show signs of a lower Hubbard band, an upper Hubbard band, a gap. And this material has also a bulk 1T-TAS2 has been predicted to be a quantum spin liquid by Patrick Lee and coworkers a few years ago. And there is experimental evidence that this material is a quantum spin liquid in bulk, but there's also evidence that it is not. a quantum spin liquid. So there's controversy here, and I believe that part of what makes this sort of controversial and complex is the interlayer coupling. And so kind of an obvious thing to try is to get rid of the interlayer coupling and just look at a single layer of the material. So it's simpler, and it's obvious thing to do once a smart person tells you to do it. And that's what Patrick Lee said to me. He pointed this out to me, and so that's really got me on this path. So what I wanted to do was look at single layer 1T TaS2, but my MBE guys would not grow it because MBE guys hate sulfur. It contaminates their chamber. And so they said that but they love that selenium. MBE guys love selenium. So they said they would make 1T TaSE2. And I said, sure, great, because you always do what your grower tells you to do. And so what we did was we used MBE to grow single layer 1T TaSE2. And the way we did that was to take a silicon carbide wafer in ultra high vacuum, and you heat it up, and that grows bilayer graphene on the surface. Then you evaporate tantalum and selenium to grow the single layer material. And the reason we use MBE is because that gives us nice, clean, beautiful surfaces, in very clean, that we can look at with our STM tip. And the growth was done by Ziek Shen at Stanford in collaboration with Sungkwan Mo at the Advanced Light Source at LBNL. And they grew the material and gave it to my group. And then we looked at it with STM, and this is what we saw. This is a typical STM image. The dark blue here is the bilayer graphene. The light on the bottom, the light blue part is the single layer 1T TaSE2. The white part is taller. That's the bilayer region of 1T TaSE2. If you zoom in on the single layer region, then you see these blobs, and these blobs, each blob here is a single star of David. There are 13 tantalum atoms in each of those blobs. It turns out that it's actually hard to see the individual atoms with the STM, but it is easy to see them with non-contact AFM, as I show here in this data. This is an image that we took by putting a single carbon monoxide molecule on the tip of our NC AFM, and then by scanning, we can see the atoms very quite clearly. These are selenium atoms, and they have the appropriate structure that you would expect from the conventional structural interpretation of this material. We then performed STM spectroscopy on the single layer material, and this is what we saw. This is a STM spectroscopy. It's a plot of differential conductivity, DIDV, which you can interpret as sort of like a density of states, so really a local density of states, because it's at the site of the tip, the STM tip. And here the voltage you can think of as energy. 0 is always the Fermi energy in an STM measurement. And so you can see there's a nice gap at the Fermi energy. And so this is an insulator, and the gap is about 100 millivolts, depending on how you define the gap. So that's nice. It's an insulator. But is it a Mott insulator or is it a band insulator? Which is it? So that's not totally obvious. And so let's take a look at it. So let's consider the unit cell. It's a Star of David. There are 13 atoms, tantalum atoms in the unit cell. Each one brings a single d electron to the unit cell. And so the question then is, where do all those electrons go? So to try to answer that, you can do a band structure calculation. And so that's what our theoretical collaborators did. Stephen Louie and Amy Liu and their co-workers. And so here I show the band structure that they calculated. Now to interpret that sort of complicated looking band structure, what's going on is these peripheral atoms, there's 12 atoms here, bring 12 electrons to the unit cell, and those 12 electrons fill up 6 bands, 6 tantalum bands here that I've highlighted in pink. That leaves that one guy, the center guy, brings 1 electron, and that electron goes into that flat band on top. And because there's only 1 electron per unit cell, that flat band becomes only half filled. So then we expect a metal. So DFT gives a metal for this material, just like I show you here. But it's not just any garden variety metal, because you notice that top band is really flat. The width is only about 20 millivolts, whereas if I put 2 electrons into that band, I expect them to repel each other with an energy on the order of 2 electron volts. So that means that the ratio of the width divided by U is really tiny, much smaller than 1. And so that means that this is in the Mott insulator regime. So we expect Mott behavior. Now, a problem is that it's hard to calculate the electronic properties of a Mott insulator using ab initio. There is no good theory of Mott insulators that we, not yet. But we can still get a rough idea of what's going on here by performing a rough approximation of the behavior by doing a DFT plus U calculation, by adding U by hand, and then doing DFT, which our theoretical colleagues did. And when you calculate this material using DFT plus U, then you do indeed get an insulator. You get a nice gap. And if you calculate the density of states using DFT plus U, then you get this plot that I show on the bottom. And it actually looks surprisingly close to what we measure experimentally. You get this nice lower Hubbard band, a upper Hubbard band, and the gap of roughly the right size. And in fact, if you look at the theoretical wave functions from DFT plus U, it kind of matches. Here I show the theoretical DFT plus U wave function, the local density of states for the lower Hubbard band compared to what we measure experimentally for the lower Hubbard band up here, and they match pretty good. But if you start looking at the upper Hubbard band, then the agreement falls apart, which is not surprising because we don't expect DFT plus U to account for all the correlations in this material. And in particular, you can see that the experimental image has a depletion of local density of states in the center of the Star of David, whereas the theory puts a bunch of local density of states in the center. And if you go to slightly higher energy, then you can see that sort of the opposite happens, where the theory, DFT plus U, predicts a depletion of L dots at the center of the Star of David, whereas experimentally we see a bunch of L dots there. So what we think is happening is that there's additional electron-electron repulsion happening at the center of the Star of David that's pushing state density up to higher energy, essentially splitting the upper Hubbard band. Now, this is just a detail, but I just wanted to mention it to you. But what we have here is a Mott insulator. So we have a frustrated lattice. We have a 2D Mott insulator. And so the last question then is, do we have localized spins? Do we expect localized spins, but can we see evidence for spins in this material? And in order to address that issue, we decided to use the Condo effect. And so I will remind you what the Condo effect is. The Condo effect is what you get when you put a localized spin on top of a metal, and then the spin of the itinerant metallic electrons will scatter the local moment, and you get spin flip scatter according to this Hamiltonian up here, and that causes a Condo singlet to form. It induces a many-body bound state to form, which has a binding energy equal to the Condo temperature, and that Condo singlet screens the spin of the local moment. And the electronic signature of that singlet is a narrow resonance at the Fermi energy. And in fact, we saw that many years ago, back in 1998, and many STM groups have seen that. And so a question that you can ask is, okay, well, what if we take a Mott insulator and put it onto a metal? Can the same thing happen? And you might expect it to, because look, the itinerant spins of the metal are going to bounce off of the spins of the Mott insulator. Now, if the Condo coupling is stronger than the exchange coupling between the spins, and you would expect the spin flip scattering to occur. And then if the Condo binding energy is stronger than the exchange coupling between the spins and the Mott insulator, then you would expect them intuitively, at least, to get screened by Condo singlets, as I show in this little cartoon. Now, it turns out that people have actually simulated this behavior using more sophisticated, actual sophisticated theoretical treatments, such as this dynamical mean field theory calculation performed by Helms and coworkers, where they basically calculated what happens when you put a Mott insulator on top of a metal, and they basically saw what I just described to you in my little cartoon. They saw a Condo effect at the interface, and which goes away as you go deeper into either the Mott insulator or the metal. So we decided to use this technique to look for signatures of the spin in the Mott insulator. And so what we did was we grew a single layer of 1T TSE2 on top of a single layer of 1H TASE2. Now, 1H TSE2 just is the same, has the same stoichiometry as TSE2, but the structure is different. Instead of the octahedral coordination of the tantalum, it has this trigonal prismatic coordination. So it's a different material, and it's a metal. And so we grew it by tweaking our growth recipe, and this is what we saw. This is the data, and here in this STM image, you see this region is 1H TASE2, and if you zoom in, you see this structure, which is a famous 3x3 charge density wave. And if you do STM spectroscopy on it, then you get up here in the upper right, you get this metallic density of state. So it's a nice metal. And we published a paper on this a few years ago in the lower left. And now if you move over here to the 1T TASE2, then you see the familiar Star of David CDW. It looks bigger because it has 13 atoms. And it also shows that nice Mott insulating behavior in the spectroscopy here in the red. But then if you go over here on the right, we have the 1T layer on top of the 1H layer. In STM, you see the Star of David CDW, but in the spectroscopy, you see something completely different. In the spectroscopy, we see this narrow Condo resonance at the Fermi energy, a signature of Condo behavior. And if we look across the surface, we see this Condo resonance everywhere we look. And furthermore, if we perform a temperature dependence of this spectroscopic feature, then we see the characteristic temperature dependence of the Condo resonance, which broadens according to this expression in the lower right. So that is so this is our data, and so this is evidence for Condo behavior with a Condo temperature of about 60 Kelvin, and so that's evidence of spins, local spins in the 1T TSC2. So now that we've shown that we satisfy these three criteria, now it's time for us to go and actually look for direct signatures of quantum spin liquid behavior. And the way that we do that is we take our 1T TSC2 layer and we forget about the 1H TSC2. We don't need that anymore. So let's get rid of that. And we put our 1T TSC2 on top of the graphene bilayer, on top of the silicon carbide. And we do very careful spectroscopic maps of the local density states at different energies. So here I show the data. Let's first look at the energies very far away from the Hubbard band band edges. So here, let's look at energies very high in energy on the right and very low in energy on the left. And when we take our spectroscopic maps at those energies, we see this periodicity that you see in the images. And that periodicity is the periodicity of the charge density wave. It's the Star of David periodicity. And if you do a Fourier transform of it, you get these Fourier transform peaks that I've circled in red and labeled with a B. And those are the reciprocal lattice vectors of the Star of David CDW. And notice that you don't see any long wavelength modulations in the Brillouin zone. So this hexagon in red is the Brillouin zone of the CDW lattice, of the CDW triangular lattice. And there's nothing going on there. And if we look at way low energies down here, there's nothing going on there either on the left. We just only see the Star of David CDW. Now let's look at energies closer. Now let's look at energies closer to the Hubbard band edge. Let's look down here. And now what we see is the image looks different. We see this long wavelengths modulations rise up out of the surface. You can see it with your eye. And if you take a Fourier transform of this image, then you'll notice there are some new periodicities that rise up and that have longer wavelength and that are living inside of this Brillouin zone. I have circled them in blue. Here you can see them, and I label them with ICS, which stands for incommensurate superstructure, because they're incommensurate with the lattice. And if we look at lower down in energy here in this Hubbard band region, it looks a little different by eye, but if you do a Fourier transform, you can still see the long wavelength modulations at that same frequency, spatial frequency, the ICS. Now let's go into the lower Hubbard band, the filled states, and again, we see that incommensurate superstructure circled in blue, but we also see a new periodicity forming, which I've circled in green at the corners of the Brillouin zone, which we call the CS, which stands for commensurate superstructure. Now here's a zoom in so you can see this a little bit better. And what we notice is that if we look at this incommensurate superstructure, if we image it at different energies, then the wave vector does not change, but the amplitude does. The amplitude of the Fourier component changes. And so here I show the energy dependence of the amplitude of the ICS Fourier component, and the strength of it. And here on the bottom, I just show the local density of states, the normal STM spectroscopy. But here on top, I show the amplitude of that ICS Fourier component. And you can see that it's very strong, big, in the region of the Hubbard band, but as I go away from the Hubbard band edges, it falls and it goes down. It gets very small. Okay, so when we saw that, it was really weird. We did not know what that was, and we were really confused about it. And so we thought that maybe it had something to do with the fact that we have a silicon carbide graphene interface, which for aficionados, it's known that there's some weird stuff that happens at that interface. You get some long wavelength reconstructions. And so we did the whole experiment all over again by growing the material on HOPG, graphite, single layer 1T TSE2 on graphite, because then there is no reconstruction. And sure enough, we saw the same behavior. Again, we saw the ICS behavior, this incommensurate superstructure, but we saw an additional feature as well when we grew the material on graphite. We saw these new periodicities arising at the M point of the Brillouin zone that I've circled here in purple. So now we have these two long wavelength modulations, the ICS and the Q sub M. And so the question then is, what the heck are these things? You know, what is going on? What is causing these long wavelength modulations? They're very unexpected. And so I think you know the answer. The answer is it's a quantum spin liquid. That's what's causing it. But before we can jump to the exotic explanation, we have to rule out the conventional explanation. We have to first make sure that it's not something more boring. So let's talk about the boring explanations and see if we can rule those out. And so the first conventional explanation is that it may be this is conventional electronic quasi-particle interference. And that's a well-known effect to STM people. Basically what happens is if you have some electronic structure, then if you have an electron that can scatter from one state to another and have a change in momentum delta K, which means that the potential that the electron is scattering provides that momentum, then what happens is you can have interference between the initial state and the final state, which leads to a standing wave on the surface that has precisely that momentum, that wave vector of the transferred momentum. And you can see those things in your STM. That's a well-known effect. But as you can imagine, these standing waves, this QPI, is very strongly linked to the electronic structure of a system, so you can actually predict it, you know, from a calculation. And so that's what our theoretical colleagues did. They looked at the electronic structure of 1T TSE2 to see if there's any possible frequencies, spatial frequencies at this QICS and Q sub M wave vectors, and they saw nothing. So there's really nothing in the electronic structure that should lead to this. So we think that QPI does not explain this observation. So another possible explanation is that it's a Moire pattern. We all know about Moire patterns these days. It's a very hot topic. Moire patterns are what you get if you take two 2D systems and you put it one on top of the other and you twist them a little bit, then you get a beating pattern. And so if you take 1T TSE2 on top of graphite or graphene and you twist it, then you do not get these periodicities. So you can show that. So that doesn't explain it. So then you might think, well, what about the Moire pattern, you know, with the underlying silicon carbide interface reconstruction? That actually could give you these frequencies, but we ruled that out by doing the experiment on graphite, and we saw the same behavior. So we feel very confident that what we're seeing is not a Moire pattern. So then you might think, well, what about strain? What about weird CDW physics? Could that explain it? Well, we feel that there's evidence against those interpretations as well. For example, we do not see these long wavelength periodicities in the lead, the low energy electron diffraction. We do see the Star of David in the lead very clearly, but we don't see these periodicities in the lead. Also, you should consider the energy dependence. The Star of David is observed at all energies. Every energy we look at, we can see the Star of David, but these new long wavelength modulations only occur at energies near the Hubbard band energies. Also, consider the temperature dependence. When the Star of David CDW is observable all the way up to room temperature and beyond. Whereas if we warm up to 77 Kelvin, these features disappear. So they have a very different temperature dependence than the Star of David CDW. And in addition, we feel that there is no signatures of strain in this system. We see no signs of strain. And in fact, when you grow van der Waals materials by MBE, it's very famous for not having strain. It's a very low strain system. You have to actually work hard to get strain in those systems. So we think that those conventional explanations do not explain our data. So then the question is, what does explain the data? And what we believe we're seeing is quantum interference of spinons on a spinon Fermi surface. And so to understand how that might occur, let's go back to this picture that I showed you earlier, where when an STM tunnels electrons into a quantum spin liquid, the electrons have to break up into two particles, a spinon and a charge-on. And so, as I said, the rate of electron tunneling is going to be proportional to the product of those two wave functions. And what that means is that the energy of the electron that it tunnels has to be split between the spin-on and the charge-on. That's where the energy goes. And so what that means is that if I tunnel into the band edge of my Mott insulator, as you see here, right into the band edge, then what that means is that all my energy of the electron goes into the charge on, because we need all that energy to overcome that gap, that Mott gap. And what that means is that there's no energy left over for the spin-on. So the spin-on has to come in at zero energy, and zero energy is the Fermi surface. And so that what that means then is that if I tunnel into the band edge of a Mott insulator, I should be directly probing the Fermi surface of the spin-ons. And so that's a way to access it if I actually have a quantum spin liquid. And so the next question to ask then is, what do I expect the spin-on Fermi surface to look like? Well, luckily, some smart people have thought about that, thank God. Patrick Lee and coworkers, for example, have published a few papers on that a few years ago. And here I show the results of their work. They use density matrix renormalization group theory to simulate the behavior of a quantum spin liquid on a triangular lattice. And they did this calculation to simulate the behavior of 1T TAS2, but it turns out that our material parameters are so similar that this simulation is also relevant for our material, which is 1T TASE2. And what they found from their calculation was clear signatures of a gapless quantum spin liquid that has a Fermi surface, a spin-on Fermi surface, and that spin-on Fermi surface has a Fermi wave vector of 0.375 times B, where B is the reciprocal lattice vector of the triangular lattice. And I'm saying that because that number will become important later on. They also saw something else interesting. They calculated using the DMRG calculation, they calculated the spin susceptibility, the wave vector dependent spin susceptibility, and they saw peaks at 2kF. And that's what these little dots represent. Those are peaks in the spin susceptibility that they measured, that they calculated at 2kF. Now, that in itself is not so surprising, because whenever you have a Fermi surface, it's normal to get a peak in the susceptibility at 2kF due to the existence of a Fermi surface. That's a pretty normal thing that you see for metals in the electronic and spin susceptibility. But what's a little less normal is the fact that there are certain regions of the Fermi surface where they did not see the peak. In these regions where I put the little black circles. And so they saw no peak in the spin susceptibility at those circles, at those regions. And that then suggests that the spin-on Fermi surface is gapped at those particular directions in reciprocal space, which are these directions right here where I've shown these little gaps in the spin-on Fermi surface. So their calculations suggest that the spin-on Fermi surface is partially gapped. Now that in and of itself is not so crazy, because the idea of a partially gapped Fermi surface is a pretty normal concept in solid state physics. We see it all the time, and we have charge density waves and spin density waves, and often we get partially gapped Fermi surfaces, and these partially gapped Fermi surfaces typically arise due to the formation of density waves. And there are different types of density waves. For example, for the spin-on Fermi surface, we might expect we could have a spin-on density wave, we could have a spin-on spin density wave, or we could have a spin-on pair density wave. All three of these types of density waves are going to lead to the same thing. They're going to partially gap the Fermi surface. And unfortunately, the calculation performed by Patrick Lee and coworkers could not differentiate between these three possibilities. So their calculation did not tell us which of these three it is. But regardless, all three of them should lead to the same kind of behavior, which is a density wave that has a wavelength of 2 pi over 2kF. Well, that's the 2kF right there. Now, there's a little nuance here, and the nuance is that if we look at this wave vector 2kF, and if we stick it at the center of the Brillouin zone, as I did here, then you'll notice that the 2kF pops out of the Brillouin zone. And so what that means is that we have to then fold it back into the Brillouin zone. And so we get that band folding. And so then that suggests that the extended zone is a nicer way to look at that. And what that suggests to us is that this gapping of the Fermi surface occurs occurs due to the interaction of the Fermi surface between these 2 points, which I can connect with this wave vector P. And P stands for the primary order. So that's the wave vector that we expect for the density wave. And that's basically just the 2kF folded back into the first Brillouin zone. So there's nothing really fancy there. But of course, this is happening for, and that means that we expect then that our density wave should have a wavelength of 2 pi over P, where P I call the primary order vector. Now, of course, this is happening in all 6 directions at the same time, like I drew here, and we can pull those P vectors, those order vectors into the first Brillouin zone, as I showed there. And so these then are the primary order vectors that we expect for the density wave that arises due to this spin-on Fermi surface instability. So now we can actually start to compare this to the data. So now we have a clear prediction from the theory, and now we can compare it to the data. So here I show our data, and we can see, do we see these primary order vectors in our data? So let's look, and what we see is, no, we don't see them. Airball, they're not there. So what's going on? We don't see the primary order vectors, and instead we see these other wave vectors that I circle in blue, which occur at higher wave vector. And so in order to understand what's happening, let's take a closer look at this situation. So let's take a closer look at these 3 possibilities: the spin-on density wave, the spin density wave, the paradensity wave. And let's ask ourselves, what do we really expect to see if we have these things? So if we have a spin-on density wave, then what is waving is the density of the spin-ons. And the wavelength should be 2 pi over P, the primary order vector. And we should be able to see that because, as I said before, the STM should be sensitive to modulations in the spin-on density. But we don't see it. So that means that this suggests that this is not happening. So we believe that this is not happening because if it was happening, we think that we should really see it with our STM. On the other hand, let's consider a spin-on spin density wave. So now what is waving? The thing that's waving is the spin. The spin is going up and down with a period of 2 pi over P. But our STM tip is not spin polarized. It is not sensitive to the spin. So we should not see this. So the fact that we do not see the primary order vector is consistent with this. So our data does not rule this out. Now let's consider the pair density wave. Now the thing that's waving here is the pair order. And a pair density wave is basically when you have 2 spin-ons coupled together in a spin-on Cooper pair that has finite momentum. And so what's waving is a spin-on pair order, which has a wavelength of 2 pi over P. But when we do our STM experiment, we're only tunneling 1 particle at a time, 1 electron at a time. So we are not sensitive to the pair order. We should not see it. So the fact that we don't see the primary order vector is consistent with a pair density wave. So our data does not rule this out. But what we do see, the strange thing that we see, are these higher wave vector modulations. So why would we see, why don't we see, well, I just explained why we should not see the primary order vectors, but why do we see these higher order modulations? Well, what we believe is happening is that we're seeing secondary order. The primary order can actually lead to secondary spin-on density waves. So let me talk about that for a moment. This concept of secondary order is an idea that's actually familiar from high temperature superconductivity, where people have charge density waves coexisting with pair density waves and superconductivity. And so these ideas have come out of the high TC community. And the idea is that if you have primary order, in our case, it's quite general concept. In our case, the primary order could come from a spin-on spin density wave or a spin-on pair density wave. And the idea is that this could then lead to secondary spin-on density wave order at higher wave vectors. And these concepts have been described in, for example, review articles. This review article by Fradkin from 2015. And a nice way to think about it is using a Ginsburg-Landau framework. And so if you consider, for example, the Ginsburg-Landau free energy functional, and if you write down the simplest free energy functional that couples the primary order with the secondary order, then it looks like this. And here, the primary order parameter is this delta here, and the secondary order is here, this rho. And this is the simplest free energy functional that conserves basic symmetries of the system, such as gauge invariance and translational invariance. And so if for this simplest free energy functional, if the primary order parameter is 0, then it's very easy to show that the minimum of the free energy density is here. here at 0. The secondary order parameter is here at 0. But if we have a non-zero primary order parameter, then that induces a non-zero secondary order parameter, which comes from this simple free energy functional that I've written down here. And in order to preserve translational invariance, then the wave vector of the secondary order has to be equal to the sums and differences of the primary order. And so what that means is that if we have primary order at these red dots, then that should induce secondary order at the blue dots, because the blue dots are the sums and differences of the red dots. So now we can compare our data to the blue dots. And then it compares very nicely. We have beautiful agreement. Our data is lying exactly where you see the blue dots. Now, if you don't like that explanation, then, it is kind of abstract and, not so intuitive, this free energy Ginsburg Landau stuff. There's another way of looking at it, which is really at some fundamental level equivalent, but some people might like it better. It's a scattering picture. So the same thing happens from a scattering perspective. For example, if I consider that primary order occurring in either the spin-on spin density wave channel or the spin-on paradensity wave channel, then the amplitude, then I'm going to have amplitude at all 6 of these primary order vectors. Now, to get a scalar scattering potential, I have to square the amplitude, in which case, once again, you get the blue dots. That's just the square of the amplitude in the red dots. So you could figure that out with the pad and pencil very quickly and easily. And what that means then is that my spin-ons that are living on my Fermi surface are going to scatter off of that potential, and they're going to pick up these Fourier components. And those Fourier components will then occur as standing waves in the quasi-particle interference of the spin-ons. In which case, once again, we expect to see standing waves at precisely those blue dots, which we see. So now we are in a position to quantitatively compare our data to the predictions of the theory. So let's remind ourselves what the theory predicts. When I say the theory, I'm talking about Patrick Lee's DMRG calculations. They predict the Fermi surface instability, which leads to these secondary blue dots, that starts from a Fermi wave vector, a spin-on Fermi wave vector of 0.375 b, where b is the reciprocal lattice vector of the lattice. Now we can take our data, which I show here, and we can work backwards. We can just roll the tape backwards and then extract the spin-on Fermi surface wave vector from our data. And when we do that, we get a spin-on Fermi surface wave vector of 0.370 times b, the reciprocal lattice wave vector, which compares very nicely to the prediction that I show above. So we consider this to be strong evidence that we are actually seeing the behavior of a quantum spin liquid in single layer 1T TSC2. But there are open questions. The story is not perfect. It's not like a hermetically sealed story. There are some openings. It's not a perfect story. For example, what about the commensurate superstructure that I mentioned early on? These periodicities at the corners of the Brillouin zone that I circled in green. Those periodicities cannot be explained by the quantum spin liquid. However, those periodicities are actually consistent with what you would expect from a 120-degree rotated Néel state. So what we believe is happening is that we might have local fluctuations of this structure, and then we think we might be seeing that. So that's a possible explanation. Another open question in this story is the fact that we don't see the primary order vectors, the red dots. We do not see them. And I explained why we wouldn't expect to see them as primary order, but it turns out that even using the secondary order scenario, we would still expect to see the red dots as secondary order, because the red dots are the second harmonic of themselves. So if you square the red dots, you get the blue dots, but you also get the red dots too. So we really should see the red dots, but we don't. And so there are possible explanations. It could, for example, be a structure factor argument. Also, if we have weak long wavelength features, they are harder to see in STM, because to see long wavelength features, you need bigger samples, bigger islands, you need better quality surfaces. So we're still trying to see them. Maybe we'll see them. Also, I just want to point out that in the high TC world, people have seen examples in BISCO, for example, where people have seen the secondary order without seeing the primary order. So it's not the first time that that has been seen. Although, of course, like everything else in high TC, it's controversial. The third thing I will mention is the Friedel oscillations, the spin-on Friedel oscillations. What we see are not Friedel oscillations, but the physics that allows us to see, if the physics I'm describing is correct, then in fact, we should also see the Friedel oscillations. And this has been predicted by Senthil and coworkers, but we don't see the spin-on Friedel oscillations. And we don't know why. Maybe it's because the spin-on bandwidth is too small and our energy resolution is not good enough, or maybe the scattering is not strong enough. We're still looking for this. We have not seen the spin-on Friedel oscillations yet. Okay, well now it's time for me to conclude. I'll conclude by saying that we observe evidence for a gapless quantum spin liquid on a triangular lattice. And for the future, we hope to see other interesting spin-on behavior, such as spin-on Condo effect. We want to perform electrostatic doping of a single layer quantum spin liquid, and there's other things to study as well. Here, let me show you my collaborators and funding. This work was funded by the Department of Energy as well as National Science Foundation. There are a lot of collaborators in this work from all over the world, as you see here. I don't have time to read all their names, but I do want to read 3 names. These are the 3 people who actually took all the STM data in my laboratory. This is Wei Ruan, who was a postdoc with me, Yi Chen, who was a graduate student, and Ryan Lee, who was an undergrad, and they all worked together, but they all left. They're all gone. I'm so sad that they left during COVID. The lab shut down and they left, and now they're all gone. They've moved on to bigger and better things. So it's good for them and bad for me. Okay, that's it. Thanks.
Okay, well, thank you so much. It's very interesting that you can get that far. People, if you'd like to ask a question, here we have a question from Gang Chen. He says, pairing breaking should correspond in energy scale. Should it be visible in temperature, that is pairing breaking, i.e. the difference in the spectrum as one varies the temperature?
I see. So you're asking, the fact that we see, you're saying the fact that we see this, you're saying the fact that if we go to 77 Kelvin, then we break it. Yeah. I think that is consistent because, for example, I mean, if you look at the characteristic energy scale of which, I would say the most characteristic energy scale is the interspin J coupling in the Mott insulator. That is, the J coupling, because that sets the bandwidth of the spin-on band. And that J coupling we estimate to be on the order of, say, 5, 6, 7 millielectron volts. And so if you look at 77 Kelvin, that's, 7 or 8 millielectron volts. So I think it's consistent because as we go to 77 Kelvin, we're going to an energy scale that's greater than the spin-on bandwidth. So I think then the idea that would kill this effect is consistent in my opinion, if that makes any sense.
Okay, thanks. Another question from Ashvin. Nice talk, Mike. I had a question. Can we rule out a conventional magnetically ordered state, perhaps with an incommensurate wave vector P in the monolayer TASE2? ?
Is that Ashvin Vishwanath?
Yes.
Aw, Ashvin, we miss you. Damn, Harvard guys stole you away. Okay, sorry. Okay, an unconventional magnetic state, is that what he's asking? That was the question.
Yeah, an incommensurate wave vector P in the monolayer.
Well,
or he's saying a conventionally magnetically ordered state is the first part of it.
Well, I mean, I guess I don't know of any predictions for such a state. The only state that I know of is the 120-degree rotated nail state, which you do expect to occur. That's going to be, you expect that to be energetically very close to the quantum spin liquid ground state. So we do expect fluctuation. I would expect the 120-degree rotated nail state, but I'm not aware of any other states that I would expect that have been predicted. So I guess my answer is I don't know. So if you have a great idea, Ashvin, then please let me know.
Okay. Other questions? You can type them into the chat or the Q&A windows. I'll wait a few seconds here. Okay, another. Philip Kim. Have you observed any charge transfer between substrate to the TASE2?
Yeah, okay, that's a good question. And there's some more reasons for that question too. Or I don't know if Philip Kim knows. I don't know what Philip Kim knows and what he doesn't know, but I will just mention that there is a paper by this guy named Yeom, who's in Y-E-O-M,
Oh, yeah.
who's in Korea. And so he has a paper, I think it's on the archive, where he says that 1T TASE2 is not a Mott insulator. And we believe that he is wrong for a variety of reasons. And one reason is that in his picture, it requires a huge amount of charge transfer from the TSC2 layer into the graphene. So, so his picture. So I'm sort of taking Philip Kim's question. I'm doing a riff on that question, just to sort of lead, to this Yeom guy. So for Yeom's alternate picture to be true, then you would need significant charge transfer from the TSC2 into the graphene. And I won't get into why that is true, but that, so if this system is not a Mott insulator, then you would expect that to occur. And so we did check for that. And so I actually have the data somewhere. If I can go through all my slides, we actually checked for it somewhere. Is this it? Yeah, so we actually can test for the charge transfer by doing STM spectroscopy in the here where my cursor is, that's the bilayer graphene. And as we go close to the monolayer 1T TSC2, we would expect, if there's charge transfer, we'd expect significant shifting. We would expect some shifting of the Dirac point in the graphene as we go close to the 1T TSC2. So we checked for charge transfer and we did not see it. So this is data indicative that there is no charge transfer. And just to convince you that that's true, there's another system that we have studied that has significant charge transfer, which is monolayer F4 TCNQ, which I show here. This is a system where you do have charge transfer. And indeed, as we go closer to this layer, which has significant charge transfer with the graphene, we do see a shift in the Dirac point. So this is something that we feel quite confident. So we feel quite confident that there is no significant charge transfer, which we feel invalidates Yeom's argument.
Okay, thank you. One last question by typing on Q&A or chat. Okay, if not, thanks so much. Very interesting talk, and we appreciate it.
Yeah, my pleasure. Thank you.
Thank you so much.
Bye-bye.
Bye-bye.
Bye.